So here in section D, we're looking at solids of revolution. Solids of revolution. First of all, I want to define what in the world this thing is. And then I want to actually develop the formula, because if you understand the formula, it's really not terribly difficult, okay? Especially since you are given the formula on the formula booklet. You don't have to try to remember it, you just have to know how to use it, okay? So, first of all, what is a solid of revolution? It's a solid that's formed by taking a piece of a function like this, okay? We have this, this function f of x here, and we're going to take a piece of it from a to b, okay? And you guys know that the area under the curve is given by the integral, okay? But we're taking this shape, and then what we're doing is we're spinning it around the x-axis, okay? And you can see what ends up happening is we get, in this case, this like cone-shaped, this flaring cone shape. It's like a bell of a trumpet or something like that. Okay? So we started out with this basic function, then we spun it around in 3 dimensions, spinning it around the x-axis, and we're able to then find the volume of the entire thing. Okay? Because we have this solid that we're dealing with. Okay? Does everyone understand what we're trying to work with?
Yes.
Okay. Now, you may have done little things where you take maybe a piece of paper and you cut it out and then you tape it to something and you spin it between your hands. And if you spin it fast, it kind of looks solid. Or you may have seen someone, maybe a magician or whatever, take a ring and they spin it around real fast and it looks like a solid ball. That's kind of the idea of what we're doing here. We're just revolving it around this x-axis. Okay? Now, I want to start with something that we know how to find the volume of and relate it to the situation here. And this will actually help us develop our formula. Now, we're going to do a couple examples, and I'm going to give you guys a chance to work on a couple of examples as well. Okay? So let's start with a cylinder. Okay? If we're looking at a cylinder, we could picture it. So let me draw. Here we go. Here's our axis. You gonna let me draw or what? There we go. Here's our x-axis. Here's our y-axis. Essentially, what we have for a cylinder, you know the formula is the area of the base times the height, and since the base is a circle, we know that the circle is pi r squared times the height, okay? So we could see a cylinder as, say, a radius like this that's then revolved around the x-axis, right? Now, we know we're going from one point to another, and I'll actually even throw in a little bit of dotted line here so we can kind of see what's in the background. All right. Okay. So here's the base of this thing. That part's in the background. But our cylinder has a particular height. In other words, it's going to be so far from one of the round bases to the other, okay? So here's our other circular base, but the radius on a cylinder is going to stay the same, okay? And then, of course, we have the other side here, and there's our cylinder that we're working with, okay? we could see this as a solid of revolution if the function we were dealing with was simply a horizontal line. Here's our horizontal line, and the reason why it's horizontal is because we don't want the radius of our cylinder to change, do we? We want the radius to stay the same, okay? What would I give the equation, what would I use as the equation of this line? It's a horizontal line, right? Y equals whatever r is, right? Y equals whatever r is. Okay? So I got y equals r. So if I were expressing the volume here, I could change this as pi times y squared times the height. Okay? Now, we want the height to go from some point here to some point here. I'm going to call this A, and I'm going to call this B. All right, so our height is B minus A. Right? You guys agree with that? Mm-hmm. Okay. Now, I now have pi times y squared times b minus a. Okay? Now, you might remember that b minus a, when we were dealing with the horizontal line, the area here under a horizontal line was found just by taking whatever that line was and multiplying it by b minus a. That was an integral. Okay? So let's take a step back here, and rather than using this b minus a, I want to actually look at this problem slightly differently. Okay? Instead of looking at the height specifically, what I'm going to do is I'm actually going to consider area. All right? And I'm going to consider area in the form of little discs. Okay? I'm going to cut this into little discs like this. So here's one, another one. Now, can anyone anticipate why I'm doing this?
You're just going to multiply
The area
the area of each sort of disc.
Okay.
but we don't really know how many discs we have.
We don't know how many discs we have. Do you remember?
Aren't we approaching infinity or something?
Okay, the number of discs is going to approach infinity, which means the height of each of these discs is going to approach
Infinity.
well, zero.
Yeah, zero.
Okay. So it's really, we're taking the limit as the height of each of these approaches zero, which occurs as the number of discs. Why isn't my eraser working? The height is going to approach zero as the number of discs approaches infinity. And what I'm going to be doing is I'm going to add up from I equals 1 to n all of the areas. The areas are pi r squared, or in this case, pi times y squared, and I'm going to do a y sub I, so it's each y for each of these, right?
But how are we going to know how many circles we need?
Well, that's the nice thing about this. We don't have to know how many circles we have. Okay? Because the number of circles, or the number of disks, is approaching infinity. Okay? Now, we want to do this from A to B. You might recognize this, the limit as n approaches infinity of the sum from I equals 1 to n. That was defined as what?
I remember seeing that, but I don't
Take a wild guess. What's our whole unit on? That's an integral, okay?
remember. Oh,
That right there, remember that's how we define the integral.
That's the wild card.
Oh.
Okay? So check this out. We're taking the integral. That's what that limit as n approaches infinity of the sum from I equals 1 to n. We're taking the integral of pi y squared. Okay? And if I only want the volume going from A to B, I'm going to take the integral from A to B. So notice here, this is why I give you this, pi y squared, that's just the area of a circle. That's why I said this formula is actually pretty easy to remember. Pi y squared, okay? That's how the IB book gives it. You might also, if you're looking elsewhere, you might see it pi times f of x squared, okay? So it's the integral from A to B of pi times whatever your function is,
X or Y?
dx.
But
Y is a function of x,
Oh, okay.
okay? So you're integrating with respect to x.
69 degrees.
Yeah, I froze in a while.
Okay? So, looking at our formula, we had seen it on the formula booklet back there. Here's our formula for a volume of revolution. Notice here's your pi r squared. Why did I pull the pi out of the integral?
So you don't have to integrate it.
We don't have to integrate it because pi is a, it's a number, it's a constant, okay? It's a constant. So, I cut off the top here. So there's our formula that we need to deal with, and you can see here a similar concept. It doesn't just work for a cylinder, it works for anything.
Well,
Okay.
what happens when it changes the size? Like on that one, the radius. If the radius increases.
Yeah.
Well, yeah, the radius is changing because notice back here, when I developed it, we were working with a horizontal line,
Yeah.
right?
Well, so now we just use super or something?
So the horizontal line didn't change at all. But it was still, that was just because that's how the function was defined. Alright?
We just find the slope of change.
Yeah, and this is why we have to do the sum, because this disk has a different radius than this disk, and this disk has a different radius, and this disk has a different radius. The radius is changing, so that's why we're integrating the function, okay, from A to B. Alright? Now notice, this gives us the volume from one point to another. As we revolve it a full 360 degrees, or a full 2 pi, about the x-axis.
So we're gonna integrate the function of y.
We're going to integrate y, which is a function of x.
Yeah, that's what I mean.
Okay? So like for example, in this case, y equals x. We're starting with a very basic one, y equals x. Okay? So, using our formula, see ya. So using our formula, we're going to, if we want to find the area, or the volume of this part of a cone, Alright, this is a cone, but it's got the top cut off, so it doesn't go all the way to a point. Alright? So,
I'll think.
what integral are we going to use?
Well, you're gonna go from 4 to 1.
Okay,
1 to 4.
integral from 1 to 4 of,
Isn't the pi outside?
okay, we can put the pi outside or inside, it doesn't matter. What are we integrating here?
Is it the
Y equals X.
The function y equals x. So whatever y is what you're going to put in here and square. Okay?
Isn't y?
Y equals x.
Oh,
So it's the integral from 1 to 4, pi times the integral from 1 to 4 of x squared dx. Okay? So that's pi times
X cubed over 3.
x cubed over 3, good, evaluated from 1 to 4. Okay? So we have pi times 64 over 3 minus 1 over 3, which happens to be 63 over 3, which equals 21. Okay? So this equals 21 pi. And since this is volume, it would be units cubed.
Two pi 4. Another question. Is that so? Okay, so is revolved through 2 pi?
Revolved through 2 pi just means we're revolving around a full circle all the way around the x-axis. Okay? If it only rotated it once or halfway around, it wouldn't, we would have to do a proportion then.
So it
Okay.
will automatically be 2 pi.
Yeah, I mean, if we really wanted to, like if we wanted to only revolve it over halfway around, we would just find the volume and then cut it in half. Yeah. Or if we only wanted to do a quarter of it, we could just divide it by 4 or whatever
Okay.
the proportion is. Okay, we're not going to mess with those, but it wouldn't be too hard to extend it to that. Okay. Let's try another one here. Okay, find the volume of the solid formed when the graph of the function y equals x squared for x between 0 to 5 is revolved through 2 pi about the x-axis. Alright, so let's take a look at what we're doing here. Here's our function y equals x squared. It goes through the origin, and then over here at 5, it's up at 25, right? So 525. So here's our curve, and we're revolving this area right here around the x-axis. So it's actually going to create kind of an interesting thing. It's going to look like this big old cone that kind of flares out like this. Okay? That's the best I can do. Alright? So that's what that'll look like. So what volume will this actually have? Well, how would we set this up? Integral from 0 to 5.
Of x squared.
Good. X squared squared. And there's a pi outside. Okay? So, pi times, what's the integral of x squared squared?
X to the 5th over 5.
Good. That is the 5th over 5. evaluated from 0 to 5. Well, 0 is 0. Okay, so 5 to the 5th over 5 is just 5 to the 4th, so that's 625. So 625 pi cubic units. Okay? So it's not too bad, right? Not too bad. So what I've done, I've given you a couple here just to practice with. Okay? You can try some. We've done a couple like these, you know, AC and E with just a plain power for X. If you want to try some of these other ones, you know, that would be good. One thing to remember, don't forget to square it in the integral. Okay? So when you do y equals x to the 3 halves, you've got to square that x to the 3 halves. All right? When you do this x plus 1 over x, you have to square that, which means you're going to need to do what? Since there's no chain rule in the integration, when I square x plus x, 1 plus x.
Two separate integral, right?
No, wouldn't have to.
You just turn it into ln of x squared or
No, you have to square it before you integrate. So when I do this, I'm going to have to FOIL. I'm going to have to FOIL. Okay? So be careful with that. Then there's some others. And you can use, here it's telling you to use technology, meaning you can't actually do the integral by hand. So set up the integral and then use your calculator to help you. And by the way, notice for B it's saying through 360 degrees, so make sure you're in degrees for part B. Okay. Then there's just some other practice here. Okay. So you can try some of these and ask questions. All right.